So in this numerical, when a circuit was given and we have to frame and solve the node equations of the given network and hence find the total power consumed by the passive elements of the network. Okay, so here this node C was assumed to be the reference node, and the at node A and at node B, Ohm's law was applied to the respective branches, and we have received the equations of I1 and I4. And in the branch AB, VA minus VB upon 0.5 gives us I2, and I3 was obtained from the branch AC using Ohm's law, and I5 was again based on the potential difference and Ohm's law. I5 was calculated, which was 20 minus VB upon 1, and KCL was applied at node A and B, where some of the incoming currents and the outgoing currents were made equal. So we have seen that we have received these equations, and when the number of equations and the number of unknowns are same, we can solve them to get the values of voltages and current, or you can say the potentials which were available at point or node A and B, and the currents. And in the end result, we can see that the current I2 was obtained as minus 3.5, which signifies that the direction of the current is different or opposite from what we have supposed. Okay, so these are the currents, and if we want to calculate the power consumed by these resistance, some of the power consumed by these resistance, then we will apply the formula I square R, and we will add all those power consumed by the passive elements or the resistance. I square, I1 square resistance, whichever resistance is receiving whatever current, we will calculate the I square R formula from this. Okay, and then we will add to get the result 266.5 watts. Okay, so here there is again a small little problem. So sometimes a circuit diagram is given in the numerical itself, sometimes we have to draw ourselves. Okay, so this is the diagram which is given, in which the C is the reference node, and there are two battery sources of the given polarity as shown, and again we have to apply the KCL and the nodal voltage theorem to get the desired results. Okay, so first of all, at node A, we will be calculating the equation. So here we can see that at node A, I1 is equal to 12 minus VA upon 2. 12 is the battery source, A is the node. So 12 minus VA, or the potential difference between the nodes, is equal to the drop across the resistance which is in the series. Here it is seen that the resistance which is in series is given below the voltage. So if the resistance is below the voltage or it is above the voltage, it is same, it is series, it is in series. Okay, so at that hardly makes any difference. And either the resistances may be given, or sometimes the internal resistance of the source is given, as in this case. So that resistance is also considered to be in series with the battery source. In both these battery sources, 10 volts battery and 12 volts battery, it is applicable. So current is I1 is 12 minus VA upon 2. And if we closely see that A node and B node, the branch which is connected between the A node and B node is not having any resistance. So we can assume that these A and B nodes are equipotential. Okay. So when they are equipotential, it means that VA is equal to VB as written here. Okay. So in the second equation, I2 is equal to 10 minus VB upon 1. 10 minus VB is the potential difference. When it is divided by 1 or applying the Ohm's law, we will get the current flowing from the 10 volt battery. Okay. And both these currents are flowing in the 10 ohm resistances. So at B, I1 and I2 are incoming currents and IL is the outgoing current. So applying the KCL here, we get IL is equal to I1 plus I2. Now applying the nodal equation, nodal theorem in the outermost portion of the circuit, we get VB upon 10. VB minus VC, you can say, but again, VC is at zero potential. So VB upon 10 is equal to IL, or the load current. Okay. So here we have 5 unknowns: VA, VB, I1, I2, IL, and 5 equations. When we solve these equations, we will get the unknown values.